All right, so I think we'll get started. So welcome everyone. Today it is my great pleasure to introduce Dr. David Ramirez, who comes to us from the Brown Theoretical Physics Center. So from the East Coast, so thanks for joining us at the later time zone. So Dr. Ramirez received his bachelor's in physics from MIT. He then received his PhD in Stanford, so out here in California, in physics. He then stayed in NorCal and worked as a postdoc at UC Davis at the Center for Quantum Mathematics and Physics before heading to his current position, as I said, at the Brown Theoretical Physics Center. So today he'll be telling us about his work from black holes to superconductors. So take it away, Dr. Ramirez.
Great. Thank you for the kind introduction and the invitation to speak. So yeah, it's great to be at least virtually back in California. I miss it. It is likely much warmer there than it is here. So, yeah, so today I'm going to give a quick overview of some kinds of things that I think about, which could be a little fun. So hopefully everyone has a good time today. So we're going to be talking about black holes and some lessons we can learn from black holes and how we can try to apply these lessons to kind of really exciting quantum systems. And so in particular, superconductors is kind of a big problem or it's a very exciting problem in modern condensed matter physics. And so the hope is to try to see if we can shed some light on some confusions in modern quantum systems. So let me first set the stage by kind of going over, quickly, the kinds of quantum systems I'm talking about here. So quantum physics is meant to be a particular class of quantum systems. And so what are the quantum phases that I'm going to be interested in today? And so I like to start by imagining kind of a very simple system. Let's say, a box with a bunch of H2O molecules in it. So at sufficiently high temperatures, this box of water vapor, steam, really just consists of a bunch of small H2O molecules drawn here as little black dots, if you can see them, and they have velocities. And at sufficiently high temperatures, basically these molecules kind of behave independently of one another. They zoom around, they bounce off the wall, they bounce off each other very rarely, but the high temperature phase is essentially characterized by the fact that it's very much kinetic energy dominant. Most of the molecules are kind of independent of one another. They just have a lot of kinetic energy and they zoom around and do their thing. And so then we can ask, okay, as we lower the temperature, what happens to this box of H2O molecules? Well, if we lower it a lot, so like really cool down to extremely low temperatures, then as we know, the H2O molecules will crystallize, form a crystalline solid, which we refer to as ice. And so in this low temperature phase, the H2O molecules like to happily line up, form a nice coherent grid. It may not be a square lattice as I've drawn here, but roughly speaking, we have some kind of a lattice with H2O molecules sitting there. And in distinction with the high temperature phase, the low temperature physics is really kind of potential energy dominated in some sense, right? The potential energy, the interactions between one molecule and its neighbors kind of tell it that it should sit in a particular location. And, it can thermally like oscillate. It can shuffle around a little bit from its kind of favorite, its home, but roughly speaking, is kind of fixed in place. And so I think, as a kind of a fun theoretical puzzle, we can ask if we had some intelligent observer who took a box of H2O molecules, or at least simulated a box of H2O molecules at high and low temperatures, but had never actually seen H2O in their real life. The question is, would they be able to predict, say, the liquid phase, right? The liquid phase is somehow intermediate between kinetic energy dominated and high energy and potential energy dominated. There's some competition between the kinetic energy and the potential energy in a liquid phase that makes it, in many senses, a bit slippier more slippery to get your handle on. And so the kinds of quantum phases I'm going to be talking about today, and what I hope to kind of gather some lessons about, is what we call kind of strongly interacting matter, or phases of matter where there's really kind of a lot of competition between kind of competing tendencies, right? So in this water analogy, right? At high energies, your kinetic energy dominated. At low energies, your potential energy dominated. And a liquid is somehow competing between those two things, and you get interesting physics. And really, the hallmark of this kind of strong interactions, strong competition, another way you can maybe think of it is that it's somehow strongly quantum. You're somehow far away from a simple classical picture. And really, the issue here is that our kind of conventional tools to really understand observables in that kind of a phase don't work anymore. And so, this isn't necessarily a purely theoretical or abstract question. This is really motivated by the fact that, over the past few decades, at least, there have been, many exciting discoveries, both in the realms of, say, condensed matter or solid state physics, and high energy particle physics or cosmology, where, here's a list of, a couple of different examples where, in some sense, all of these have components that are strongly interacting, that there's a lot of competition, and we don't have really good theoretical tools to address, say, your high temperature superconductors. That's been an open question for a couple of decades now. Strange metals are metals that behave strangely, surprisingly enough. And so there's really kind of a lot of rich physics that we don't necessarily have the theoretical tools available immediately. And so really physics, when it comes to solving problems, is you have a collection, you have various collections of different kinds of tools to attack different problems, and each of them will be valid in different regimes. And so I like to think of it as, we have a bunch of different streetlights, and we're able to look underneath a given streetlight and try to understand some physics. And so, some examples would, like, if we have, say, a semi-classical system, which, we could say is very close to a classical system we understand well. We have tools, things like perturbation theory, where we turn on a small effect and see how that small effect induces corrections to kind of the naive answer. But we have plenty of other things like a handful of exact solutions, some numerics. They're very useful when we have them, but they're also very hard to come by, or they're costly in the case of numerics. But really today, what I'm going to be focusing on is this slightly bigger circle over here called duality. And so we'll talk quite a bit more about what duality really means as we go along. But for the one sentence for the moment is roughly that duality is saying there's some freedom in how you choose the variables you use to solve a problem. And as we're familiar with in many situations, picking the right variables can make all of the difference. And so duality is about trying to find the right variables with which to organize your thinking about a problem. And so today we're going to be talking about a slightly peculiar duality, which goes under many names, things like holography or gauge gravity duality. These are maybe words that will become slightly clearer as we go along, but basically, the punchline is that certain classical gravity, certain systems, certain classical gravitational systems are in fact exactly dual. And dual, I mean in this kind of a complicated change of variable sense. They're dual to these strongly quantum phases we were talking about before. So strongly quantum systems where there's no kind of dominant, it's not like the high temperature phase of water. It's really kind of, there's strong competition between various ingredients in the problem. And so we don't really have kind of direct attack on these quantum phases. But the kind of magic of the duality is that we can turn it into something that looks completely different, but we are able to make a little more progress in actually analytically solving for some properties. And so this is a rather bizarre duality. So hopefully my goal is to try to motivate it a little bit and in particular, see how we can use it to learn some things about, say, a superconductor or many body physics. And so just very briefly, the plan for today is I'm going to be going over, some facts about black holes. So we'll spend a good amount of time just talking about kind of what does Einstein's theory of general relativity tell us about black holes. And once we have a little bit of kind of black hole technology under our belt, we'll move on to discussing duality, and in particular this gravitational duality here with so this ADS we'll get to later. And then once we have a handle on the duality, then we can try to talk about some applications, and we'll look at a couple of lessons I think we've learned that I think are of value for strongly interacting quantum systems, independent of the duality. So the goal is to get some lessons that maybe we learned in this kind of very special corner of physics, sitting under this streetlight. But the hope is that maybe we're getting some lessons that are really more valid generally. Great. So when thinking about black holes, I like to start thinking classically. And so I think that there's an interesting historical tidbit that you can kind of get some of the characteristic scales for black holes out by this kind of Newtonian thinking. And it's really kind of motivated from a very simple idea that I'm sure many have looked at in their mechanics classes. Namely, let's say I have some planet and I want to launch a projectile and get that projectile, send it off to infinity. How do I send a projectile from the surface and send it all the way out to infinity? And this is a kind of a straightforward energy conservation problem. And if you solve this, then the answer you'll find is some expression like this. The speed that you're going to travel at is determined by the mass and the size of the planet you're on. So roughly speaking, you should kind of think of this as a little bit like a density sitting in here. It's not really a density because there's no 3 there, but it's morally a density. So denser objects will have a larger escape velocity. And so for the Earth, this comes out to a number 11 kilometers a second. And really kind of a question that can be asked and was asked a few hundred years ago, in fact, late 1700s, by these gentlemen here, is, are there any objects that are sufficiently dense so that light could not escape from them? So importantly, physicists at the time had already known that light travels at a finite velocity, so there's a finite speed of light. And then really the question is, can we pack everything into such a small region that the escape velocity you would need to get away from that object is greater than the speed of light? And if you take the expression I had before, and rearrange, you'll find that as long as your mass is kind of compactified in a small enough region set by this radius here, then that object is what these folks called a dark star. So they didn't have the words black hole at the time. They called it a dark star, which is also a pretty good name. And of course, I didn't mention here, but this is of course a very famous picture of a black hole we've actually seen and measured, and it's an exciting time to be thinking about black holes because we have so many exciting experimental apparatus kind of coming online at this time, I should say. And so, yeah, before I move on to kind of the general relativity part of the story, just one quick warning that the escape velocity is escaping to infinity. So there's going to be a difference when we talk about black holes, where black holes are about not escaping from a compact region, whereas this is slightly different. So the concepts are not exactly identical classically and with GR, but they're similar. But with that out of the way, let us go actually to general relativity. And so I unfortunately don't have time to really get too much into the weeds with general relativity here. But so this is a quote here by John Wheeler. It says, roughly in a sentence, GR works out as So space-time, the geometry in which we live and interact, tells matter how to move. Essentially, gravity is the curvature of space-time that dictates how matter will travel in it. And then the matter itself kind of tells space-time how to curve, right? So if I have a very massive object, it's creating a lot of curvature in the space-time around it that kind of creates the apparent kind of gravitational forces we see. And so here, matter, we mean kind of anything that carries energy and momentum. So matter is energy and momentum. And so I kind of, there's kind of a fun Spanish pun here that I like. So in English, pienso luego peso is roughly, I think, therefore I weigh. And so weigh as in weight, as in mass. So I think, therefore I weigh. So I think as in there's some matter, there's some energy and momentum moving around in my brain. There's neurons firing. And that energy, that information, because of general relativity, then has a mass. Not really. It has some curvature associated with it because matter tells space-time how to curve. Yeah. So that is, GR in a couple of sentences. But really, all we're going to need is the fact that, light is deflected by massive objects because a massive object creates a bunch of curvature. And then that curved space tells the matter, the light in this case, which directions it should be going. And so all we need is that, gravity affects light, which is not something that's very obvious from a Newtonian perspective, but Einstein really taught us how to think about that correctly. And really the only other fact I'm going to need for today is just that there's a universal speed limit in our universe and the theoretical universes we will be considering, which is that nothing can travel faster than the speed of light. And so it has this number in SI units. The number is not so important, but really just the fact that there is a maximum speed that any object can attain. And so, famously, GR is a little bit, mathematically involved. It's a bit complicated. Einstein, it took him a good number of years to kind of sort out and work out all the math. And he was not super optimistic necessarily that people would be able to actually take his equations and find, simple, clean solutions. But quite remarkably, only a few months after Einstein's publication, Carl Schwarzschild had wrote a letter to him describing a solution he found that describes the geometry outside a spherically symmetric mass, right? So again, we could imagine in this picture, we have some mass m here. This mass will distort the geometry around it, which causes the deflection of light. And so what Schwarzschild gave is descriptions of the geometry surrounding this mass here. And it took a little while for this to be realized, but this was also the first time anyone wrote down the geometry that describes a black hole from the exterior. This is something that it took a while to really appreciate. So this was around 1915. It wasn't probably closer to, I think, 50s, 60s, and beyond that we really feel like we got a good handle on black holes. But nevertheless, this was written down very early on. And again, just historical aside, the fact that Schwarzschild did this while he was in fact fighting in World War I always am amazed by. But yeah, so let's talk a little bit about black holes in GR. So we're going to imagine kind of a situation where there's some mass, say over here, somewhere inside this region. It's very dense. And so all of it is contained within that Schwarzschild radius we had talked about before. And so we want to ask, okay, if we're an observer, standing far away, what do we see? Well, what we can do, and what this diagram is meant to depict, is that if we're sitting at the vertex of these two cones here, then the two cones are telling you kind of which directions signals can propagate either to you or away from you. So if I'm standing at the cone and I want to shoot either a message to a friend or send a light signal to somewhere out into space, then it has to lie somewhere within this cone. So this is a consequence of the fact that the speed of light is finite and nothing travels faster than the speed of light. So I can't send a signal from here out here because that would require me traveling too far of a distance in too short of a time. That would require a larger velocity. And so again, we have the time direction moving up, and this, I guess, would be the radial direction along the bottom. And so when we're far away from the mass, there's nothing very exciting going on with our light cones, our signal propagation. But as we get closer to the mass, which again, remember is over here, as we get closer, these light cones start to tilt, right? And so now I used to be able to send a signal, maybe somewhere out here, somewhere around here, but as you get closer and closer to the mass, the geometry is getting more and more curved. There's more curvature, more warping of space-time itself. And so the signals get affected by this warping. And this really becomes most pronounced as we approach the horizon. And so once you cross the horizon, in fact, your light cone is completely tilted to the side, roughly 40, 45 degrees here, so that no matter what signal you send out, the finite speed of light, causality is always going to tell you that your signal will never get outside of this horizon radius, right? So everything within this blue region has to go towards smaller r. And this effect gets more pronounced as we go further and further inside the black hole. And so eventually, there's a singularity at the center, and life gets complicated and probably messy. But yeah, so the idea here, right, is that this horizon really forms a surface of no return, right? That once you cross through the horizon, no signals you send out can get back to your friends at infinity, right? So you're over here and you're sad because you can't talk to your friends who are back at it. And I should say that these Schwarzschild radii are kind of fantastically small. So so yeah, it's good to have a sense of the scale of the numbers in the problem. But if we compress all of the Earth into 9 millimeter radius, that's a pretty dense object. So, but nevertheless, some theorems proven later in kind of black hole revolutions really told us that, okay, these are in fact, they are astrophysically relevant because there are many situations in which a collapse into a black hole is inevitable. There's nothing you can really do to escape it. So eventually, this mass will form a black hole. And so it really is worth trying to understand them. And again, just another quick little warning here. I'm going to ignore essentially anything that goes on inside the horizon. There's all kinds of fun, paradoxes and interesting kind of hints at what quantum gravity really means. But we're going to push all that to the side for today and just think about the life of external observers. And so what would such an external observer see? So, okay, here's a artist rendition or built on simulations of what a black hole could look like. And so, the first thing we like to do is, perform some experiments on this black hole. We want to measure some properties of this black hole. And so to do so, we would like to have, say, a lab that we could set up. And so I would stand in my lab and I would do my experiments and measure stuff about the black hole. And the first thing my funding agency would ask me is, okay, how much is this going to cost? Which will depend pretty heavily on how much fuel do you need, right? If you're standing here, then you're going to feel kind of a gravitational attraction towards the black hole. So you need some rockets to kind of keep you from falling in. Right? And so a natural question that you have to confront if you want to, say, perform experiments on a black hole is, how hard is it for me to stay kind of hovering above the horizon, right? So if I had some rockets here, or if I had a friend off at infinity who was holding a really long string, how hard would he have to pull to make sure that I don't fall into the black hole? So it's pretty important if you want to, say, survive and publish your results. And so this is quantified by an object called the surface gravity, and it's denoted kappa. And the first interesting fact about kappa that I'm going to call, in fact, the zeroth law, is the fact that kappa is constant no matter where you're sitting. Right? So if I'm over here, if my lab is over here, if my lab is over here, they all are just as hard, roughly, to hold in place. And so that's convenient, and it's a curious fact, so we make sure to note that. But now we want to really start doing our experiments. And so the first thing we're going to do is we're going to very slowly lower something, very adiabatically, very cautiously drop something into the black hole. And so we do this, we say take our yo-yo and let it drape down, and eventually we'll fall into the black hole. And what we observe is that, okay, we've thrown some mass into the black hole, so there's more mass in there now, so the mass increases. But the black hole also gets bigger, right? It's eating, so it's gotten a little bit bigger because it just ate some new mass. And in fact, what you can show using Einstein's equations is that the increase in mass is always directly proportional to the increase in the area. And so, that's a kind of nice feature, and it holds very generally for all kinds of black holes. And so this is an interesting fact. It's both intuitive, but it's also very general. And so now we get a little bored with our slow adiabatic experiments, and we decide to really just start chucking stuff into the black hole, as violently as we want. We can throw whatever we want in there. And the next thing we observe is that, in fact, the area of that black hole will always increase no matter what kind of process or what we throw into the black hole. No matter how we do it, it will always increase the area. And so to summarize, we have these three interesting facts that we've learned through our experiments with these black holes, namely constant surface gravity, this relation between the change in mass and change in area, and the fact that the area is always increasing. And as this is slightly spoiled by my title here, there's a very strong resemblance to laws of thermodynamics if you have taken some thermodynamics before, right? So the 0th law of thermodynamics says a constant temperature, and for a system in equilibrium, it has a constant temperature. The first law tells us, first law is essentially just energy conservation. So in this form, this is a statement of, you increase the energy, it's related to the heat produced or added to the system. And the second law, probably one of the more famous ones, is the fact that the entropy always increases in a thermodynamic system. And so just real quick, a couple of words about entropy. So entropy is kind of a thermodynamic observable that really is meant to quantify kind of our ignorance of microscopic details. Right? So given some macroscopic system, we can measure, say, a temperature or pressure, but we don't really have a fine-grained information about where each molecule in our gas is. And so here are a couple of examples of, well, first, a low entropy state where, I put everything in one corner, I put all the gas in one corner of the room. And if we remove kind of the barriers and let the system evolve in time, you would expect that after some late time, you would move towards a state where the gas is all dispersed evenly, roughly throughout the room. And so the left is kind of an example of a low entropy system because, so it's low at least compared to the right-hand side, which is higher entropy, because there's a lot more configurations with the dots spread randomly throughout the box than there are configurations with the dots spread randomly throughout the tiny corner. And so, yeah, again, really, this, you could also just, imagine this as a picture of time evolution where you start with a low entropy state, you're going to go towards the high entropy state. You would be very surprised if you started with the gas evenly distributed throughout the room, and then at some later time, it manages to all pocket together in one corner. That would be very bizarre and unfortunate. So luckily, physics tells us that's pretty unlikely, astronomically unlikely. But yeah, so we have kind of these interesting facts, and really the takeaway here is that it's pretty suggestive, right? That maybe we should think of mass like an energy, maybe we should think of temperature like the surface gravity, and maybe we should think of the entropy like an area. So These are all kind of surprising facts. Well, maybe not so much mass and energy. Einstein had already taught us that mass is a form of energy, so that's less surprising. But I would say the other two are quite surprising. For, again, this is solving classical Einstein's equations, right? There's no, I haven't considered a thermodynamic ensemble in gravity. I'm just considering here's a black hole as a solution of Einstein's equations, and it has these properties. So that's quite perplexing, and people weren't quite sure of how to really interpret it. And then Hawking came along a short time after these discoveries and realized that, in fact, with just a sprinkling of quantum mechanics, so there is an H bar here, so you do need a tiny bit of quantum mechanics, but with that, an external observer will in fact feel radiation coming from the black hole. It'll feel a black body spectrum of radiation, it'll feel thermal radiation with this temperature. And again, set by the surface gravity, but there's all these constants, so you have to be a little careful. But so once we have those constants for the temperature and surface gravity relationship, we can then figure out what is the entropy kind of associated, right? So once we know T, we can figure out what is S from this first law. And doing so, you again find some more constants, in fact, and you have what we call the Bekenstein-Hawking entropy. And so this SBH, BH is very convenient because it both stands for Bekenstein-Hawking, but also black hole. So according to your tastes. But so yeah, these are, this was, I think, really revolutionary in Hawking's work, was demonstrating that, okay, maybe there is something a little more concrete to these kind of black hole analogies with thermodynamics. And again, to get a sense for the numbers here, we have that, okay, for a solar mass black hole, so the mass of our sun, that is a pretty astronomically small number. So this temperature is very, very small, right? Again, it's proportional to h bar. H bar is a small number. And similarly, the entropy for a solar mass black hole is much larger than the current thermal entropy of the black hole. So these temperatures and entropies are kind of, they're at a very different scale than the things that we're used to in everyday life. And again, that usually comes down to some factors of h bar and g, in this case, are both very small and so on. But this was all thinking about kind of equilibrium properties, quote unquote, equilibrium properties of a black hole. Namely, thermodynamics is for systems in equilibrium. There's a lot we can do kind of moving beyond equilibrium and really think of kind of this horizon, right, the surface of the black hole, as a kind of fluid with, a temperature, entropy, and going beyond equilibrium, you can associate a diffusion constant, you can associate viscosities, you can associate conductivities. So it seems like Einstein's equations seem to want to tell us that the horizon behaves like a fluid to an external observer. And so, this picture is meant to illustrate that if I were to say, think of the horizon as a fluid and I were to throw a pebble into the black hole, I would imagine there should be some ripples emanating from where that thing came in. And we should be able to kind of describe that. And in fact, people have been able to do that. And so really, this is all very kind of interesting, very intriguing. It's been, one of the puzzles in, say, gravitational dynamics for decades now. And really the question is there any way we can think of it as more than analogy, right? Is there anything really kind of hidden in this thermodynamics and hydrodynamics? And so now we get to our second theme, which is duality. And so duality, as we're going to go through in a couple different stages here, but to begin with, I think most conceptually, this notion of a Gestalt switch or a Gestalt shift. Right, so here I imagine a lot of folks have seen this picture, which at the end of the day is just a bunch of black and white pixels on a screen. But depending on how you look at it, you look at the black pixels as the foreground, then you see a vase. You look at the white pixels as the foreground, you see two faces looking at each other. So it's really just a matter of perspective, right? But at the end of the day, it is just one image, right? It's just one thing, and how you interpret it, you're free to interpret it in different ways, and those could either be useful or not. And so that's kind of, I think, the key idea to keep in the back of your head with duality. But a little more quantitatively, I think the perfect example is if you have to integrate some function over, say, the xy plane. I can divide the xy plane into a bunch of little cubes or little squares and integrate that way, or I could change variables in my integrand and integrate over, sum up a bunch of little kind of angular wedges. But it's the same thing, right? I'm computing the same quantity. You should get the same answer if you're doing things correctly. And so it's really just a matter of convenience. And that is really kind of at the heart of duality. And so another kind of more physical example would be looking at, say, Maxwell's equations without matter. And we note that if we make a substitution, E goes to minus B and B goes to E, then the equations map directly to themselves. And so Maxwell's equations are a perfectly good example of a system with a well-understood dual, in the sense that electromagnetic duality, where I exchange the roles of electromagnetic fields, preserves kind of the equations describing the system. And so in some sense, that what I call the electric field and what I call the magnetic field is a little ambiguous if there's no matter. And so you're free to kind of call one whatever you like. And yeah, so there are many other examples of duality that are incredibly useful in physics that I won't really have time to go into. But again, the real punchline here is that finding the right variables to attack a problem can it's important, because if you want to actually make progress, you need the right variables. And again, right in quotes, but it can be very surprising. And so the duality that will be important for us today is, again, what's known as it's a duality involving gravity. And so this was proposed by Juan Maldacena in 1997. And the statement is that ADS gravity, again, ADS is kind of a technical term, anti-de Sitter. It's not super important for our purposes, but a type of gravity is dual to a quantum system that has no gravity. So I think the without gravity part is kind of important here. And so the idea is, again, that we have some gravitational system G that is dual to some non-gravitational system T. And kind of the picture here is that so ADS is really just saying I put my gravitational system in a box. It's a very convenient kind of covariant box to use in GR. And so for our purposes, the duality is really telling us that a very complicated quantum system that we may not have the tools to attack, say, with traditional quantum field theory techniques. Say this could be a collision at a high energy particle collider. It creates some really strongly interacting plasma that we don't know how to talk about very coherently. Well, maybe we could feed it through a kind of a duality black box that translates that strongly interacting quantum physics into a classical gravitational story. And so the idea is that maybe we can take questions on one side, translate it over to the other side. We get some gravitational problem that maybe we have a better chance of solving. And then once we have the answer, we can feed it back and translate it back into our original quantum language. And so the virtue of this, which I guess depending on your optimism, is really the idea that the duality really maps easy questions on one side to harder questions on the other. So when this quantum system is really tough to solve directly, to really attack directly, then the gravitational side, if it exists, is going to be easier to deal with. And conversely, right? So when the gravity is really strongly interacting on this side, then that maps to a very, in some sense, easy quantum theory on the other side. So, yeah. And so, let's maybe get a little more in detail about how does this mapping work? What is this black box, this duality black box in this setting? And as you maybe have guessed, the black hole thermodynamics that we spent a good amount of time talking about 10 minutes ago or so turns out to in fact be the literal thermodynamics of our quantum system, right? So we have this quantum system T, and our black hole has some thermodynamics associated with this horizon over here. And the statement is the thermodynamics of this horizon is really the thermodynamics of this soup on the right-hand side. And so there's kind of a match between the entropy on one side and the entropy on the other side, temperatures, et cetera. And so, this is already teaching us something quite fantastic, which is one of the big mysteries from just directly the gravitational side is, what is this entropy? What is it really counting? But in the context of this duality, when this duality applies, then we have a very concrete understanding of where the states making up that entropy are. They're just the states of this quantum system. They're rearranged and packaged and translated through our dictionary, but we still have a kind of one-to-one mapping. And yeah, so there's a lot we know about the dictionary, but there's also a lot we don't. So I'm only going to list a couple of things. But before we were talking about maybe what is the non-equilibrium version of a black hole, what is the non-equilibrium version of the horizon doing? Well, if you pass it through our dictionary, then this turns into just honest fluid mechanics, right? Navier-Stokes equations, right? So there really are secretly hidden in Einstein's equations some Navier-Stokes-like equations governing the fluid mechanics of that horizon. And that translates directly into the fluid mechanics in our quantum system. And yeah, so a slightly more microscopic version of this fact is that the graviton, the actual the bending of the gravitational field really maps to kind of the stress energy tensor, which tells you about Hamilton, say energy densities or momentum densities in our quantum system. And if our gravitational system also has, say, an electromagnetic field floating around, so if we have electromagnetism in our box as well, then that translates in our quantum system into a conserved charge, right? So we have a conserved current in our quantum system, and so there's a mapping between conserved charges on one side and dynamical electromagnetism in the other. And so again, the punchline here is that this duality is saying that certain classical black holes, again, emphasize classical, are secretly identical. Again, and through a very complicated change of variables, they are identical to finite temperature quantum systems and quantum systems that are behaving rather exotically. And so there's some value to being able to look at classical dynamics to understand strongly quantum physics. And so let's really get into what we can do with this. So let's say we wanted to find a superconductor. And so are there conditions under which we can make our black hole dual to a superconductor? And so to do so, the first thing we should do is, okay, how do we measure the resistivity of our quantum system? So in the lab, this is, okay, probably technically involved, but I'm a theorist, so I can just say in words, I'm going to connect some leads and put a potential difference, so I apply some voltage difference to the system, and I measure, say, the current that passes through my two leads or the heat generated by this current running. So how can we do this in our gravitational setup? So we want to find kind of the gravitational picture that corresponds to plugging in some leads and measuring resistivities. And so what we do is we take our black hole in a box. And so again, this is the wall of our box. And we apply an electric field along the wall. And so we attach some leads, we apply an electric field. What this does is this starts sourcing an electromagnetic field. So we can picture that as some photons, falling in from the wall of the box. And just like any wave propagation, this electromagnetic wave is going to come from the wall of the box, and it'll reflect off of the horizon, and some of it will be absorbed, right? So that we'll have a blue piece that got reflected, and we notice that our horizon has now absorbed the other piece of this infalling photon. And so this increasing area means we have an increasing entropy, which means we've generated heat, right? So the fact that our system is heated up a little bit means that our black hole has gotten a little bit bigger because it swallowed the photon that came from the battery. And so this is kind of the gravitational picture of resistive heating, which is kind of a fun picture. And so how do we try to get a superconductor? Well, all we need to do is try to prevent that photon from falling into the black hole. And so the goal is, how can we prevent, when I turn on this electric field, the photon from actually reaching the horizon? Well, we just need to put a shield. We need to put something in front of the horizon that will prevent it from getting absorbed. And so we need to add an extra ingredient. This is, it's not pure gravity that's doing this, but it's gravity with some extra matter. But that's not terribly important for our purposes. But the idea is we paint some reflective coating on our black hole, and now when we send in a signal, it gets reflected back. There's still a reflected component, that's perfectly fine, but the black hole does not grow in size, and so there's no heat generated, so there's no resistive heating in this holographic set. And so I think when you put equations behind all of these pictures I'm drawing, you get honest superconductivity, right? You really get exactly zero resistivity. You get all of the properties you expect of a superconductor, and probably not too much of a stretch to say this is an unconventional superconductor, in the sense that Bardeen, Cooper, and Schrieffer did not talk about black holes when they wrote down their wave functions. So this is at least unconventional in that sense. Great. So the next thing I want to look at, just real briefly, as we approach the finish line here, is classical chaos, or chaos in general, both classical and quantum. And so classical chaos, I imagine some folks have maybe seen either in popular literature or in their classical mechanics courses, but one of the hallmark effects of classical chaos is what's referred to as the butterfly effect, where if I take two trajectories that are initially closely separated in phase space, say, so I have two trajectories, or let's say I start with a point and I take another partner to that that's very close, starting very close by, and I time evolve both of them. Then we see what happens in a chaotic system. Time evolution makes these two trajectories that started very close by to diverge exponentially. And so this divergence grows exponentially in time, and this means that there is kind of an associated exponent governing that growth that we refer to as the Lyapunov exponent. Again, a little technical, but the basic idea is, right, the phrase that goes along with this is, let's say a butterfly flaps its wings, makes some small initial perturbation in Tokyo, say, and then in New York, you end up with a hurricane as a result. So climate systems are very famously quite chaotic. And so initial perturbations can get amplified quite dramatically in the climate system, climate physics. But this was a relatively recent concept in classical physics, and it's even more kind of, I think there's even more to explore once we start throwing in quantum mechanics. How does quantum mechanics enrich the kind of chaos story from classical mechanics? And so what we're going to do is we're going to show a quick little gravitational cartoon of what chaos looks like from the gravitational perspective, and see what we learn by translating it back into kind of more traditional quantum mechanics. And so in our gravitational picture, let's imagine we have our black hole. I turned it on its side. So this is, again, our wall. And so let's imagine, we're an observer sitting near the wall, and we look at our black hole. So maybe there's some radiation coming out to us, but we gather some measurements, and then we take our measurements, we log them all, and we come back the next day. So we did our experiment for that day, mission accomplished. We come back the next day, and now we do the same experiment, except 6 hours before we do the actual measurements, we throw something into the black hole. So we take some dirt, some pebble W, we throw it into the black hole. What's going to happen? Well, we know that the black hole will get a little bigger. There'll be some non-equilibrium phases, right? So non-equilibrium physics, I should say. This W will spread out along the horizon, cause some ripples that disperse, and then 6 hours later, we go back and collect our measurements again. So the question is, how has the addition of this light particle thrown into a black hole affected our measurements at this later time? And so, kind of the physics here is that as we throw in our W particle, it'll start creating little ripples on the horizon. And so there's a notion of, how quickly is W being spread out over the horizon? How quickly does it diffuse across the horizon? And this is, a question you can answer. And when you translate kind of this picture back through our duality towards just a regular quantum mechanics, what are the observables that correspond to this diagram, the sketch I've given you, this cartoon? It turns out it's an observable that we haven't really considered very often in quantum physics. It's slightly exotic, but it's still tractable in certain cases, and we can define a quantum analog of this Lyapunov exponent. So I think this was one of the first instances of defining a sharp quantum Lyapunov exponent for kind of general situations. And beyond that, with a little more effort, it was realized that this quantum Lyapunov exponent is in fact bounded, in the sense that there is an upper bound on how chaotic a system can be. So this has no analog in classical physics. This is really, you can see an H bar down there, right? This is really a quantum phenomena, that there is a bound on this Lyapunov exponent. And I should say this, this was pure, quantum field theory, right? Pure quantum mechanics, pure QFT. There was to derive this result, this bound, there was no need to resort to this gravitational picture at all. This was a purely quantum mechanical result. But really, we only stumbled upon the definition of lambda Q by studying black holes, is basically my punchline here, that this is a pure result in kind of generic, strongly interacting quantum systems that we don't ever have to talk about black holes for. But to even talk about this observable, we were motivated by black holes. And so really, the goal is that, I hope this illustrates the value of this kind of incredibly abstract duality picture, but nevertheless, we at the end of the day get kind of very sharp results in quantum systems that I think are quite fascinating. But yeah, so let me just conclude real quick here. So just a quick summary. So I hope I've convinced you, at the very least, that black holes have some interesting properties. These thermo and hydrodynamic properties of black hole horizons have kind of been a guiding light in a lot of gravitational or a lot of research in, say, quantum gravity. As in, we hope that quantum gravity will give us clues into understanding these thermo and hydrodynamic properties. And indeed, we've talked today about some dualities that do tell us what these properties really mean. What does the black hole thermodynamics mean for black holes in ADS? Well, it means that this black hole, you're really describing the thermodynamics of the dual to that black hole. And so, and then really the program I'm kind of emphasizing today is to use these black holes as kind of toy models to understand physics we're interested in for other purposes, right? So for condensed matter physics, say, could we learn anything about mechanisms for superconductivity at strong coupling by looking at some of these black holes? Or I really haven't gone into today at all the kind of quantum information side of the story, but there's been a wealth of insights both into black holes and into quantum information coming from this interplay. And similarly with kind of more traditional high energy theoretical physics, this duality promises to be very exciting. And so some future directions, just real quick, this dictionary it's a very complicated change of variables to translate a black hole into this quantum system. And I think there's a lot we could learn about, mapping observables through our black box. We don't really have the best handle on it yet. I think, especially if one wants to kind of apply the lessons that we're getting, directly to some concrete physical system, I think it's a bit premature for that. I think this is very much an abstract, or very much a theoretical, these are theoretical experiments we're running. But if down the line we wanted to really apply our gravitational insights directly in some physical system with a known gravitational dual, then we need to know which quantum systems have kind of coherent, useful gravity duals. And that's an open question. We have some necessary conditions, but there's a lot of, we certainly do not have a necessary and sufficient list of conditions to impose to make sure that a given quantum system has a useful classical gravity dual. And, kind of perhaps most excitingly is this last bullet point, where you can imagine if we solved bullet point 2, we know exactly how to construct a material that has a coherent classical gravity dual. Well, then we can use that material that we can build to learn about quantum gravity in these kinds of contexts. And so we can use the duality the other way, right? Going from superconductors to black holes, roughly. But yeah, so I think there's a lot we have learned about quantum gravity from this duality, and I think there's plenty more to go. But yeah, I think I'll leave it for here, and I'll just say yeah, thanks.
All right, so on behalf of everyone, thank you so much, Dr. Ramirez, for the excellent talk. So I'm sure if we're in person, everyone would be giving you a big round of applause. So I'll just do it for everyone. So I noticed there were actually some questions in the Q&A that were during the talk, which in retrospect, maybe I could have interrupted you, but maybe if you don't mind going back a little bit, can you see the Q&A?
I can.
So I'll, so in case.
Yeah, so let's see. So yeah, I'm seeing a question here from Paul Fisher. Let's see, I'm going from outside to inside the black hole, my let cone is tilting. So yeah, so it's not that you're yeah, so sorry, there are signals that I can send. Let me actually maybe try to go back to the slide here. So the fact that these cones are tilting is really just this kind of the statement that a light signal is getting bent by the curved geometry. And so this picture is slightly misleading, but so the idea with these cones is that anything inside this blue region, so anything you send at a velocity that is less than the speed of light, will lie within this blue region. So everything must be sent at a velocity smaller than the speed of light. And so every signal that goes in this region has a smaller speed, has a smaller velocity. Sorry, I don't know if I answered that question super coherently, but yeah, so the tilting of the cones doesn't say that you're going faster than the speed of light, but the cones are just kind of telling you which directions the signals you send get pulled, roughly speaking. And so Joel, David, that is a fantastic question about area and not volume. That is, so this is referring to the fact that the Bekenstein-Hawking entropy depends on the area and not the volume. That is a fantastic $1 million question that guides a lot of research. So there's kind of a big point about this duality I haven't really emphasized, which is that it's holographic in nature, in the sense that, sorry, in our box picture here, there's a sense in which T lives on the boundary of this box. And so T lives in one lower dimension than the gravitational system. And so what looks like an area from the gravity's perspective turns out to be the volume from the quantum system's perspective. And so yeah, that's a great question. And another great question from Joel here. Let's see. Yes, so the qualifier some classical black holes is, again, the statement that is a bit technical, but if you're familiar with gravity, so this comes down to the statement of ADS, right? So the idea that ADS is roughly putting the system in this box, but more precisely, it's turning on a cosmological constant. And so this is gravity with a negative cosmological constant. And so that's what I mean by some gravities. I mean gravity with a negative cosmological constant. So that in principle, or just immediately off the bat, tells us these are not physical, astrophysical black holes that we should look in the sky for, because we live in a universe with a small positive cosmological constant rather than a small negative. But yeah, great question. And yeah, and so for in the context of fractional quantum Hall effect, so yeah, the fractional quantum Hall effect is a it's a strongly interacting many-body phase in 2+1 dimensional quantum systems. Just take like a layer of an electron gas and turn it in a strong magnetic field, and there's really kind of beautiful physics that comes out of that simple setup. And so I would say that there are analogs of the Hall effect that we can cook up in holography. And so in this picture, if we were to imagine that this was say a magnetically charged black hole, then that would roughly correspond to having, so there are ways to cook up some analogous features to the fractional quantum Hall effect in holography or in this duality, but the kind of canonical fractional quantum Hall effect is it's a gapped phase, so it's topological, and so the kind of the duality doesn't work quite as nicely, or it's a little tougher with gap systems. So I would say there's some analogs, but probably not very clean ones for the quantum Hall effect in kind of from the condensed matter side. But.
All right. Well, unless if there are any other questions, it's already 5:07, so we're already a little bit over. So unless if there are other questions, I think we'll stop there. So again, on behalf of everyone, thank you so much, Dr. Ramirez, for the excellent talk. And thank you everyone for coming. We'll have one more Science by Diverse Scientists 2 weeks from today. So pay attention to look out for details for who will be speaking and what they'll be telling you about. So thanks everyone for coming, and thank you again, Dr. Ramirez. Although it does actually look like there's one more question. I don't know if you have to go, David, but.
No, I do not. So yes, sorry. So yeah, I avoided using the phrase ADS-CFT because I think it's a lot of terminology I didn't necessarily want to go into, but this is exactly ADS-CFT. And so yes, a huge component of work in holography these days has been really trying to untangle the relationship between entanglement and geometry. So this was very briefly advertised here at the end with quantum information, but really this one can spend an hour talking about how exciting that is, which I don't want to assume you have, but yes. So sorry for slightly lying and not saying ADS. But.
All right, awesome. Well, thank you for answering that one last question. It just came in right in time.
My pleasure.
All right, so thank you again, everyone, for coming, and thanks again, Dr. Ramirez.